Hey students, welcome back. In this note set, we're going to take a look at photons, that is particles of light, and the energy that they carry. This is part of Unit 11, Modern Atomic Theory. Let's start by just getting a quick review, reacquainted with some of the characters that we've studied from way back in first semester. First of all, this handsome fella, Democritus, was a Greek philosopher, not technically a scientist. And his idea of the atom is important because it was prevalent for centuries. Democritus said that an atom is a solid, indivisible sphere. There's no way that you can subdivide an atom. In fact, the Greek root of the word atom means that which cannot be cut. So Democritus was working hundreds of years before Christ, so BC, and his idea of the atom lasted well into the 1800s. It was only late in the 1800s, 1895 or 6, that the character in the middle here, J.J. Thomson, produced evidence that there's something smaller than the atom, or at least within the atom there are small movable charges. Eventually, years and years later, after Thomson's experiments with the cathode ray tube, that small movable charge was called the electron. The person on the right was Thomson's protege, Ernest Rutherford. Rutherford, only 2 decades, or less than that even, 15 years or so after working in Thomson's lab, produced his own notion of the atom, which included, really importantly, the nucleus. The nucleus was the center of mass of the atom, whereas almost all of the mass is centered in the nucleus. That's not all of the charge. The charge is carried in a cloud of electrons outside the nucleus. So if you add all of that together, we end up with the conception of the atom that we left off with last semester, where we have protons, which are positively charged in the nucleus, along with neutrons, which have no charge, together in the nucleus, and a nearly massless electron, which bears a negative charge somewhere outside the nucleus. In Unit 11, we're going to blow this open a little bit. We're going to take a look at a more modern, more up-to-date understanding of the atom. And that all begins with a study of light. Now, you signed up for a chemistry course, not a physics course, but there's a little bit of physics that we ever so slightly are going to touch upon in order to develop our understanding of the modern atom. That involves a study of light. Light is really unique. It has a dual nature. It is both a wave, something that oscillates up and down and up and down, and it's also a particle. There are numerous really interesting experiments, one of which is called the double slit experiment in physics, that shows that light can behave as both of these at the same time, which is really mysterious because almost everything else is either a wave or a particle. It's not both. But light is both a particle. The particle of light is called a photon, and yet it also behaves as a wave. It can be transmitted through space where there's no other particles. Space is almost a complete vacuum, nothing in it, and yet light can travel through space. First, let's take a look at some properties of waves. Waves are oscillations, movements of energy. There's a peak and a trough in these oscillations as things go up and down and up and down. The distance between any two similar points on a wave is called the wavelength. So you could measure wavelength as the distance between one peak and the next peak. Or you would get the same measure if you measured from one trough to the next trough, or even from one midpoint of a wave to the next midpoint of a wave. Waves do travel with a velocity that you can measure in meters per second. And there's something called frequency. Frequency is the number of waves that pass a given point per second. And frequency is actually measured as per seconds. It's not really a particle, it's just the number of waves passing per second. We call that a hertz, is the unit for frequency. One goofy thing about the abbreviations. If you take a look at this symbol, it's the Greek letter lambda. That's the typical abbreviation for wavelength. The lowercase letter c is the abbreviation for velocity, as long as we're talking about electromagnetic radiation, of which light is a part. And then lastly, here's the really confusing part. This looks like a V, but it's the Greek letter nu. It does not correspond to velocity, it corresponds to frequency. So the abbreviations are all wacky. Talk to the physics people if you have a problem with that. I sure do. But if we put all that together into a nice, really useful equation, we can say that velocity of a wave is equal to its wavelength, abbreviated with the symbol lambda, times its frequency, abbreviated with the symbol Greek letter nu. Here's another really interesting fact. All waves that we're going to study in this unit are electromagnetic waves, and they travel at a constant speed, 3 times 10 to the positive 8th meters per second, which, by the way, is insanely fast. It is the fastest thing that exists in the universe, a photon of light. But everything travels at that velocity. Electromagnetic radiation is a very large, or it consists of much more than just visible light. It consists of radio waves, microwaves, infrared rays, the visible light, which is just a sliver of the electromagnetic spectrum that we happen to be able to perceive with our eyes, ultraviolet light, X-rays, and gamma rays. Different wavelengths of light correspond to different amounts of energy per photon, with this general trend. The shorter the wavelength, the higher the energy. Now that's interesting. Why would they say shorter wavelengths correspond to higher energy? Well, remember that all electromagnetic radiation travels at the same velocity. So take a look at this. At the top, we have a short wavelength wave, which if it's traveling at the same velocity as another type of wave where there's a longer wavelength, that means for the shorter wave, more waves will pass a given point per second. Aha, there's a higher frequency. And if more waves are passing a given point per second, that means there's more energy transferred with the shorter wavelength. The longer wavelength has a lower frequency and therefore lower energy. Wavelength and frequency are inversely proportional. As one goes up, the other goes down. And wavelength and energy are also inversely proportional. If we take a look just at the visible light, the small portion of the electromagnetic spectrum that we can perceive, there is again a range of wavelengths and therefore a range of energies. Starting with the longest wavelength that we can perceive, red light, and going all the way down the rainbow to violet or purple light, where there's a shorter wavelength and higher energy. So purple light has more energy than red light. Okay, let's put some math behind this. First, there was a scientist named Max Planck who discovered that matter doesn't absorb or emit just any quantity of energy. Rather, matter absorbs only discrete amounts of energy, kind of like steps. If you're going from one level of your house to another, you're going to follow steps, unless you happen to have, let's say, a ramp. If there's a ramp connecting two levels in a building somewhere, then you're experiencing a continuous change in elevation. A little bit of inch forward on the ramp, you get a little bit of elevation change. But with steps, you're either on one step or you're on the next step. The only way to change your elevation is to take a full step. Well, Planck discovered that light is like steps. Energy is gained or lost only in whole number multiples of a quantity h times nu. That's again the Greek letter nu. It looks like a V. In that calculation, h is Planck's constant. It's a really, really small number, 6.63 times 10 to the negative 34th joules seconds. That is, the unit is joules times seconds. And the Greek letter nu, which looks like V, is frequency. Okay, now check this. Planck said the energy that a particle of matter either gains, or absorbs, or gives off, emits, is always a whole number multiple of h nu. Aha! So the change in energy that the piece of matter, the particle, experiences is always a multiple of h nu. That means a photon is going to be have an energy equal to some product of h nu. All right, let's review the equation that Planck gave us and combine it with what we already know from our study of waves a little bit ago. We know that velocity equals wavelength times frequency, which if we just do a little bit of rearranging here, we could say that frequency equals velocity over wavelength. Well, check Planck's equation. In Planck's equation, you also see frequency, or the Greek letter nu. Frequency, frequency. Let's plug one of those equations into the other. We'll combine them together. If you plug in c over lambda, where nu is in Planck's equation, you get h times c over lambda. This formula is really useful, and it's going to help us calculate all kinds of things. Let's start with one fairly straightforward sample problem. A photon of light with a wavelength of 5.25 times 10 to the negative 7th meters, which is typical for visible light. Okay, we're talking really small wavelengths. So that would be 525 nanometers. Falls in the green range of visible light. Calculate the energy of a photon of this wavelength. Okay, let's use our really useful formula. Delta E equals Planck's constant h times the speed of light, represented by the c, all over the wavelength, which is this Greek letter lambda. Planck's constant, 6.63 times 10 to the negative 34th. The speed of light, 3.00 times 10 to the positive 8th meters per second, all over the wavelength, 5.25 10 to the negative 7th. Punch those numbers into your calculator, and we got 3.78 10 to the negative 19th. If we're asking for energies, which we're going to be doing in this unit, the unit is joules. Joules for energy. Okay, let's tackle another problem dealing with energy of a photon. The blue color in some fireworks is achieved by heating copper 1 chloride, CuCl, to a very high temperature. The heated CuCl emits light at a wavelength of 450 nanometers, which stated in meters would be 4.5 times 10 to the negative 7th meters. How much energy is contained in a single photon of this wavelength? Again, we'll use our equation that combines Planck's equation with that of a wave. Delta E equals Planck's constant times the speed of light over the wavelength of that light. Planck's constant is always going to be 6.63 times 10 to the negative 34th. And the speed of light is always going to be 3 times 10 to the positive 8th. What's different this time is the wavelength of light. This time, instead of green light, we're dealing with blue light, which, if you look at a picture of the electromagnetic spectrum, that'll put you somewhere around 400 to 450 nanometers, which translated into meters is about 4.5 times 10 to the negative 7th. Again, pull out your calculator and crunch all these numbers. Half of the battle, I think, is carefully typing all of these numbers into your calculator. Feel free to use sets of parentheses. And I would also point out that if you have a TI calculator, just above the 7, there's a comma button on the calculator. And if you hit second comma, if you read the lettering above the comma, it says EE. And that EE, when you hit it on your calculator, tells your calculator times 10 to the power of whatever you're going to type next. In other words, your calculator knows to do order of operations first if you're using that EE button, which means you don't have to push as many of the buttons that say times 10 to the, and then a caret, and then an exponent. So it's just a little shortcut if you're typing in a rather large expression like this into your calculator. When all it's said and done, we should arrive at 4.41 times 10 to the negative 19th. And since we're talking about energy, the unit is joules. One last problem, and this one is a challenge problem. Take a look at this one. A photon of ultraviolet light, so not quite in the visible spectrum, possesses enough energy to mutate a strand of human DNA, which is part of the reason why UV light, ultraviolet light, is damaging to our skin. So, you got to be careful with it. What is the energy of a mole of UV photons, which have a wavelength of 25 nanometers, which is quite a bit smaller than the light wavelength that we saw in the previous two problems? There's a little hint. The metric prefix nano means times 10 to the negative 9th. So we'll use the same formula as we had in the previous two problems, Planck's constant times the speed of light over the wavelength. The wavelength is 25 nanometers, or 25 times 10 to the negative 9th meters. So if we put that together, Planck's constant times the speed of light over the wavelength, 25 times 10 to the negative 9th. No, that's not in proper scientific notation, but that's okay. Gives us an energy change for a single photon of 7.96 times 10 to the negative 8th joules. A single photon. This question asked about a mole of photons. A mole can be found by taking Avogadro's number. Do you remember Avogadro's number from earlier in the year? 6.02 times 10 to the positive 23rd times the answer that we had for the energy of the single photon, 7.96 10 to the negative 18th, gives us a final answer of 4.8 times 10 to the positive 6, or 4.8 million joules. That's a lot of energy. The problems on your homework assignment won't be quite as challenging as this one, but it's fun to stretch ourselves, right?